Buongiorno.
Good morning and welcome to this new appointment with the world of aerodynamics. I'm Nicoletta Di Pascale and I work at CIRA.
Pascale e lavoro al CIRA.
You already know why an airplane flies. Today we're going to see how. I'd like to answer this question by taking you on board on a glorious Italian airplane, the Partenavia P68. We'll be together as the airplane takes off, during the climb, the cruise, the descent, and the landing. We'll learn how to react to sudden gusts or to an engine breakdown. We'll be in a real flight deck and we'll study its main controls. Are you ready? Let's go! Let's take a look at the main items of an airplane. An airplane like this, but also the B747 or a military one, can be seen as a body. The fuselage connects to the various surfaces. The basic surface is the wing, which is divided into two halves, the right wing and the left wing. On each half of the wings, there are the ailerons. Every airplane typically has a symmetry airplane, so the right and the left sides are geometrically identical. In the aft fuselage, there are the tail surfaces, the horizontal tail and the vertical tail. Just like the wing, the tail surfaces have a fixed part and a mobile one. The fixed part of the horizontal tail is called stabilizer. The mobile part is called elevator. The fixed part of the vertical tail is called fin. The mobile part is called rudder. The movement of the mobile surfaces allows controlling the flight and keeping the airplane balanced. We now can start our flight.
Iniziamo il nostro volo.
When passengers are on board, the airplane goes to the runway. Then the pilot performs a few tests, among which the engine test, and waits for the control tower OK. When everything is ready, the takeoff begins. The airplane takes off when it reaches a speed called takeoff speed, which is the speed that allows the lift to exceed the weight. From this moment on, the climbing starts. At the end of the climb, the airplane reaches the cruise altitude, at which the airplane has an horizontal position. But what actually takes place during the climbing, i.e., how does the airplane maintain its balance? On the airplane, four already known forces act: the weight, P, the lift, L, the drag, D, and the thrust, T. The lift force can be seen as a force applied at the so-called aerodynamic center of the airplane. Since the aerodynamic center does not coincide with the gravity center, a moment m arises. The moment is given by the lift force multiplied by an arm b, which is the distance between the aerodynamic center and the center of gravity. In a similar way, also the thrust and the drag will give rise to moments around the center of gravity. The condition of airplane balance means that the sum of all these forces and moments must be zero. How? The total moment around the center of gravity is balanced by a counteracting moment generated by the elevator deflection. If the sum of these forces and moments is zero,
Due to the first principle of dynamics, the airplane has a contrast straight speed
con una
v,
velocità v che
which
forma un
forms
angolo di
a trajectory angle gamma
rispetto al
with
piano
respect of the
orizzontale
horizontal Earth surface.
Dire che le forze e i momenti sono in equilibrio significa dire che la loro risultante è zero.
Let's write the balance equation in an orthogonal Cartesian system of axes, xw, yw, and zw, with the origin located at the center of gravity. The axes xw and zw are in the symmetry plane. The axis xw is in the opposite direction of the speed vector v. The axis zw is upward, and the axis yw is perpendicular to the other two axes. The plane of this drawing matches the symmetry plane. The balance equation in symmetric flight can be written: force is equilibrium along xw, thrust equal drag plus weight multiplied sine of gamma. Force is equilibrium along zw, lift equal weight multiplied cosine of gamma. Moments equilibrium around the axes yw, m equals 0. Let's make an example. Let's suppose to have a Boeing 747 with a trajectory angle of 5 degrees. The sine of the 5 degrees is 0.09. The cosine is 1. The total weight of the airplane is 400,000 kilograms. We can write thrust equal drag plus 0.09 multiplied weight. Lift equal weight. Total moment equal 0. This means that in order to maintain the airplane balance during the climb, we need a thrust equal to the drag plus 9% of the airplane weight, and a lift equal to the weight. With an efficiency L/D equal 15 and a weight equal lift equal 400,000 kilograms, for the B747, the drag will be 1/15 of a 400,000 kilograms equal 26,700 kilograms. This means that the thrust of the engine has to exceed 26,700 plus 36,000 kilograms. At the end of the climb, the airplane reaches the cruise altitude. For B747, it is 10,000 meters. By neglecting the weight variation due to the fuel consumption, the equilibrium equations in horizontal flight are:
in questo caso valgono le seguenti equazioni:
thrust equal drag, lift equal weight, moment equal 0. The ratio between the density of the air at 10,000 meters and the zero altitude is equal to 0.34. The wing surface is 500 square meters. From this data, the lift coefficient can be evaluated. It is equal to 0.6, with an efficiency equal to 15. The drag coefficient results 0.60/15 equal 0.040. Let's try this computation of our P-68. We've reached a cruise altitude of 4,000 meters. Our flight speed is 220 kilometers per hour. That is 77 meters per second. The weight is 1,600 kilos. The wing surface is 18 square meters. The cruise altitude is 4,000 meters, and the efficiency is equal to 8. In this case, the lift coefficient results CL equal to 0.35, and the drag coefficient will be 0.35/8, equals 0.040. happens when the speed decreases? What is the minimum speed that allows keeping a horizontal flight without problems? There is a minimum speed under which we cannot fly due to one of the following conditions. The stall of the wing, the engine reaches its max thrust, or the elevator reaches its max deflection angle. You are already aware of the dangers of the stall. If the speed decreases, in order to keep the lift constant, we must increase the angle of attack, alpha, until a critical value is reached that causes the airflow separation. In this condition, the drag increases and the lift suddenly drops. We've reached the limit speed for the wing stall. It may also happen that by increasing the angle of attack, the aerodynamic drag increases and a higher thrust is needed. The thrust can be supplied up to a maximum after which drag cannot be overcome. In this case, the minimum speed is due to the max
ma la
thrust.
velocità minima è dovuta al fatto che il motore ha raggiunto la sua spinta massima.
Finally, it may happen that as the angle of attack increases, so does the aerodynamic moment around the center of gravity, and the airplane starts to rotate. To balance this effect, we use the elevator, but we cannot rotate it above a maximum deflection angle. In this case, the wing has not stalled. The engine has not reached its max thrust, but the airplane cannot be balanced anymore. In this case, we've reached a minimum speed due to the elevator max deflection. Let's try to answer another question.
In volo orizzontale a quote sempre più alte.
What is the highest altitude an airplane can reach in horizontal flight?
Come già sapete, se aumentiamo la quota di volo,
the density of the air decreases with flight altitude, so does the lift.
Anche la portanza.
What should we do to maintain the same lift?
Per mantenere la stessa portanza?
It's quite simple. Either we increase the speed or the angle of attack. In both cases, however, keep in mind that you will have to face an increase of the aerodynamic drag. As we reach higher altitudes, the engine has to give more thrust. Will it be able to do that? Actually, the higher the altitude, the lower will be the thrust the engine can give the airplane. There's an altitude at which the max thrust required by the engine is equal to the max thrust the engine can perform.
Più in alto di questa quota non possiamo volare.
It is called ceiling altitude. Our Patternavia P68 has a ceiling altitude equal to 6,000 meters.
Non c'è in zona l'Himalaya.
We're near the airport, so we start a slow descent.
Lentamente la nostra discesa.
Let's see what happens to the forces acting on the airplane.
Vediamo cosa accade alle forze che agiscono sul nostro aereo.
Let's suppose we are descending with a trajectory angle equal to -5 degrees. Let's make a few calculations. The sine of -5 degrees is -0.1. The cosine is near unity. We can write the equilibrium equation. Thrust equal drag minus 0.1 weight. Lift equal weight. Moment equals 0. This time, the engine has to provide less thrust because the weight helps contrasting the drag.
La componente del peso contribuisce a vincere la resistenza aerodinamica a spese della gravità.
The Patternavia P68 is a twin-engine aircraft. Let's suppose there's a sudden breakdown and both engines stop. What do you think would happen? Well, don't worry. It's extremely improbable that both engines stop. Yet, let's suppose it happens. We would have the gliding flight. That is a descending flight typical of gliders that have no engines. The gliding flight is a flight with a thrust T equal to 0. Let's calculate the max distance we can perform horizontally with an altitude loss of 1,000 meters. By keeping in mind that the aerodynamic efficiency is the ratio between the lift and the drag,
cioè il rapporto tra la portanza e la resistenza.
And that drag equal weight multiplied sine gamma, lift equal weight multiplied cosine gamma, we can write that efficiency equal L/D equal 1/tangent gamma, where gamma is the gliding angle. Let's make some calculations. A civil airplane with a max efficiency of 15 can fly a horizontal distance equal to 15 kilometers every 1,000 meters of altitude loss. A glider instead has much higher efficiency, over 40. This means that it can fly horizontally for over 40 kilometers for every 1,000 meters of altitude loss. Before landing, let's ponder other situations. During a flight, the weight of the airplane decreases and the center of gravity changes due to fuel consumption or to the movements of people on board. Therefore, the thrust varies, like during the climbing and the descent. Such variations of weight, center of gravity, or thrust may cause variations of moments around the center of gravity. Such forces must be balanced. On a general airplane like our P-68, the variations are very small. Yet, on a B-747, they may be relevant. Taking into consideration the weight variations at a constant speed and altitude, the pilot has to lower the altitude to obtain the necessary lift coefficient. If the center of gravity varies, there will be a moment around the YW axis, which means that the nose of the airplane will be moved up or down. If a variation of the thrust is required, the pilot has to contrast the resulting moment. In these cases, either to control or to contrast a variation, the elevator is used. The elevator is used by the pilot through the control stick. If the pilot pulls it, the elevator goes up and a downlift is produced. This lift makes the airplane to nose up. On the contrary, if the pilot pushes the stick, the elevator rotates down. An uplift is produced and the airplane nose down.
Cioè il suo muso ruota verso il basso.
During the flight, we can encounter wind gusts that can be ascending, descending, or lateral.
Così come nelle raffiche laterali. Esse costituiscono un disturbo.
How can we contrast them? Does the pilot always step in? No, it's a burdensome task for him, especially during a long flight. In addition, these phenomena are so fast that the pilot is not always able to contrast them. For the vertical gusts, the stabilizer has a stabilizing role. For the lateral gusts, the fin has a stabilizing role.
Per quelle laterali, invece, interviene l'intero piano di coda verticale, cioè la deriva, e il timone di direzione in posizione fissa.
How does it work? A vertical gust is equal to a variation of the angle of attack. This variation is felt by the wing and the horizontal tail as well. This causes an horizontal tail lift to be generated and consequently a stabilizing or destabilizing moment for the airplane. If the moment is stabilizing, we say that it is statically stable under the vertical gusts. If the airplane remains in the disturbed position, it's said to be statically neutral. Finally, if the airplane goes away from the initial position, it's said to be statically unstable. The airplane usually returns to the stable conditions through an oscillatory motion. If the oscillations decrease, the airplane is dynamically stable to the disturbance. If the oscillations keep their amplitude, the airplane is dynamically neutral. If the oscillations become higher and higher, the airplane is dynamically unstable. There's a point of the airplane that if it coincides with the center of gravity, the airplane is statically neutral. Such point is called neutral point. We know that the center of gravity of an airplane can vary, yet to keep the airplane stable, it has to be always ahead of the neutral point. The distance between the neutral point and the rearmost position of the center of gravity is called stability margin. As for the lateral gusts of wind, called yaw-wing disturbances, the concept of static and dynamic stability can be introduced. The lateral gust causes on the vertical tail an angle of attack. It generates a lateral aerodynamic force that tends to nullify the trouble. Also, in this case, the airplane can be statically or dynamically stable, neutral or unstable, respect to a yaw-wing disturbance. An airplane is usually designed with a stability margin that allows it to be both statically and dynamically stable. Of course, a stable airplane is more difficult to fly, as it does not respond to all commands of the pilot. Why? Well, the commands of the pilot are like disturbances for the airplane. If the airplane is very stable, it will tend to nullify the pilot action. A funny information: some military airplanes that require a high maneuverability have low stability margins or are even unstable. We're now landing. There's a bit of lateral wind. How does the pilot contrast it while keeping track of the runway? And what would happen if an engine would fail in this moment? Don't worry, the pilot knows what to do. In both cases, he uses the rudder. The pilot moves the rudder through the pedals. The right pedal makes the rudder to turn right, and vice versa. If the rudder turns right, a left force acts on the vertical tail, contrasting the wind coming from the right. The breakdown of an engine, for example the left one, is like a right lateral wind. In this case, the pilot turns the rudder right. So, do we use the rudder to change the direction of the airplane? Yes. The airplane changes direction through the turn maneuvers, performed by using the ailerons. The ailerons move simultaneously and in an unsymmetrical way. This means that when the aileron of a half wing turns down, the aileron on the other half turns up. Let's see how the pilot makes them work. For example, by turning the stick right, the aileron on the right wing goes up and the left one goes down. This means an uplift on the left side and a downlift on the right side. This causes the airplane to turn right. The landing was successful. We've come to the end of our flight. Now you know not only why airplanes fly, but also how. Of course, we've only taken into consideration some aspects of aerodynamics. Yet, now you have all the elements that will allow you to answer many questions about the flight. I hope this has been an interesting lesson for you. Bye-bye!